Welcome to the Explainer. Today, we're doing something really fun. We are stripping away all the software layers, the operating systems, the flashy UIs, and we're looking at the absolute bare metal core of our digital world, computer organization and architecture. We are going straight into the CPU, the central processing unit. It's the ultimate brain of the computer, fetching and executing billions of instructions every single second to make, well, literally everything we do digitally possible. Okay, let's dive into this. When we call the CPU a brain, we're really not exaggerating the sheer scale of its workload. Think about it. Every swipe on your phone, every mouse click, every single rendered frame of a massive video game, it's all just this one physical component fetching a command, deciphering what it means, and acting on it. And it's doing this over and over at absolutely mind-boggling speeds. But mechanically speaking, how does it actually pull this off?
Well, here's our roadmap for the journey. 1. The brain of the computer. 2. Evolution and the power wall. 3. Measuring CPU performance. 4. The core instruction cycle. 5. Speaking in binary. And finally, 6. How computers make decisions. We're going from the macro hardware all the way down to microscopic logic.
All right, section 1, the brain of the computer. Let's peek inside the physical processor. Inside that tiny piece of silicon, you basically have 4 main components that make up its anatomy. First up is the ALU, the arithmetic logic unit. This is the calculator, right? It handles all the raw math. Then you have the control unit, which acts exactly like a traffic cop, directing all the operations using electrical control signals. Next are the registers. These are ultra-fast microscopic pockets of storage located right inside the CPU itself. And finally, the buses. Think of these as the physical electrical highways carrying data, memory addresses, and signals between all these moving parts. But here's the thing about those highways. They illustrate a fundamental physical limitation, and it's known as the von Neumann bottleneck. See, because the CPU needs to get both its instructions and its data from the memory, and they share the exact same physical bus, only one thing can be fetched at a time. It's kind of like a massive, multi-lane superhighway suddenly merging into a single-file dirt road. No matter how incredibly fast your CPU is, it fundamentally has to sit there and wait in this physical traffic jam. Moving on to section 2, evolution and the power wall. This is all about hitting the physical limits of speed. Now, we've obviously come an incredibly long way. First-generation computers, like the old ENIAC, used these bulky vacuum tubes that literally took up entire rooms. The second generation replaced those with smaller, cooler transistors. Then the third generation figured out how to pack many transistors onto a single integrated circuit. And finally, the fourth generation brought us VLSI, very large-scale integration. Today, we are casually packing billions of microscopic CMOS transistors onto a chip no larger than your fingernail. It's wild. And this whole incredible shrinking act was driven by Moore's law. That's the famous observation that transistor counts on a chip roughly double every 18 to 24 months. For decades, this law fueled an absolute explosion of rapid performance gains and plummeting costs. But recently, well, we've kind of hit a wall. The trend is slowing down, simply because we've made transistors so vanishingly small that quantum physics is actually starting to get in the way. So that brings us to a really fascinating dilemma. Why can't we just keep making processors faster forever? Like, if we can't make the physical parts any smaller, why not just crank up the clock speed so the existing parts just work harder and faster? The answer to that is the power wall. It is an unforgiving law of thermodynamics. Power is proportional to capacitance times voltage squared times frequency. And frequency is your clock speed. If you try to double the frequency to make a faster chip, the power requirement spikes exponentially. And all that excess power, it turns straight into excessive heat. Engineers quickly realized that pushing clock speed straight up would literally melt CPUs right through their motherboards. No way around it. So how did the industry bypass this thermal nightmare? Well, they pivoted entirely to multi-core designs. Instead of trying to build one scorching hot, super fast core, they placed multiple, slightly simpler cores onto the exact same chip. These cores can run instructions in parallel, and because they operate at a lower frequency and voltage, they dodge that destructive power wall entirely, resulting in vastly better performance per watt. It's exactly like replacing one exhausted, overworked draft horse with a team of 4 well-rested horses all pulling together. Which leads us to section 3, measuring CPU performance. Let's look at the ultimate speed limit equations. Now, what's really interesting about this is how we actually calculate it. Execution time is our ultimate measure of performance. The CPU time formula shows that the total time to run a program equals the instruction count multiplied by the average clock cycles per instruction, or CPI, multiplied by the clock cycle time. Let's do the math on a quick example. Say you have 50,000 instructions, an average CPI of 2.5, running on a 2 GHz clock rate. That clock cycle is 0.5 nanoseconds. To put that into perspective, that is so fast that light only travels about 6 inches in that time. Multiply it all together, and the whole program runs in exactly 62.5 microseconds. But there is a huge catch to speeding things up, and it's beautifully illustrated by Amdahl's law. Say you invent a way to make 40% of your program run 5 times faster. You'd probably expect a massive overall boost, right? Well, Amdahl's law proves that because the other 60% of the program remains completely unchanged, your overall speedup is only about 1.47 times faster. You are fundamentally bottlenecked by the portion of the task that you cannot improve. All right, section 4. The core instruction cycle. This is the never-ending assembly line. Every single piece of software, from a simple calculator app to a massive operating system, runs on a continuous, factory-like cycle. Step 1, fetch. The CPU grabs the next instruction from memory. Step 2, decode. The control unit interprets what that operation actually means. Step 3, execute. The ALU physically performs the math. And step 4, write back. The CPU stores the result. Fetch, decode, execute, write back. This microscopic assembly line loops billions of times every single second, without fail. Section 5, speaking in binary. Let's talk about how all that data and code is actually stored. Everything moving through that high-speed assembly line we just talked about is ultimately just ones and zeros. Now, unsigned numbers are pretty straightforward. They only represent positive values. But think about this. How does a computer understand negative numbers without a physical minus sign? Engineers use a brilliant trick called 2's complement for signed numbers. The bit on the far left acts as a sign indicator. To make a -5, the computer takes a +5, mathematically inverts all the bits, and just adds 1. It's such an elegant hardware workaround because it allows the chip to process subtraction exactly like it processes addition. But it's not just the data. The instructions themselves are packaged into rigid binary formats. In classic MIPS architecture, for instance, a 32-bit instruction gets sliced up into very specific fields. You have the R-type or register format, which handles math right between the registers, complete with slots for operation codes and sources. Then you have the I-type or immediate format. Use this when you need to load a raw number directly. So instead of a destination register, it dedicates a massive 16-bit block simply to hold that number right inside the instruction itself. And finally, section 6. How computers make decisions. This is where logic operations and control flow come into play. So how does a CPU use this binary math to actually make choices? At the absolute lowest level, it all starts with microscopic bitwise operations. An AND operation is used to mask or clear bits. It only outputs a 1 if both inputs are 1. An OR operation sets bits. XOR is perfect for toggling, outputting a 1 only when the inputs are different. And shifts, literally sliding a row of bits left or right, is a fantastic hardware shortcut to rapidly multiply or divide by powers of 2, without needing a massive complex math circuit to do it. And we can connect that raw hardware logic directly back to the high-level code you might write. Concepts like if statements or while loops, they don't actually exist in the hardware. Instead, the CPU relies on simple branch and jump instructions. BEQ means branch to a new address if 2 registers are equal. BNE branches if they're not. And J is an unconditional jump to another part of the code entirely. When you type if A equals B in a programming language, the compiler translates it all the way down into these tiny conditional leaps. This is how all complex decision-making is physically built. It really is absolutely staggering to think about. Every application you use, every complex algorithm running our society, every piece of digital art, it all fundamentally boils down to these simple, microscopic jumps, shifts, and fetches, looping billions of times a second inside a tiny piece of silicon. Our entire complex digital world is basically just a symphony of basic binary logic operating flawlessly at scale. Armed with this understanding of the architecture right beneath the surface, what are you going to build with it? Thanks for joining me on this explainer, and keep exploring.